In a previous video, we covered a common quant interview question regarding probability. For example, if we have a fair coin and we do the independent experiment, now on the average, how many runs in order to see the first occurrence of head, head, head? Now, some viewers ask me, would the answer be the same for a fixed pattern? Like for example, in the three patterns that we're looking for, HHH versus HTH, should the answer be the same because the coin is fair? Think about it, right? If you have fair coin for the first three trials, you have equal probability to get HTH or HHH. Each has equal probability of 1/8. So for that, intuitively, you may think the answer is the same. But the answers are different. So today, we're going to review the problem and we try to clear some misconceptions for this sort of problems. The first misconception is that when you think about the first three runs, you're going to have 1/8 probability see the pattern HTH. So on the average, it takes 8 runs to see HTH pattern, right? So what's wrong with this understanding? If you have a single run of multiple choices, for example, if you have 8-sided die, you see a particular side, for example, number 7, you have 1/8 probability, and on the average, it takes 8 times in order to see it, right? So that's the true statement if we're talking about one single outcome. But here, we'll consider 3 consecutive outcomes as a pattern. The key observation is that not all sequences are equally likely after the initial run, initial result. So, for example, if you don't get desirable pattern HTH, right, you don't have to restart again. Sometimes you can reuse the current results. So what I mean is, if you have, for example, T and H for the first 2 run, right, and then of course this does not match what we're looking for, HTH. However, you have an H, which means that you don't have to start from scratch. So it'd be possible that you have a T and H, you just need 2 additional runs in order to see the pattern HTH. So the thinking of this misconception always treat 3 as a unit, So if you play the game, like if you consider these 3 runs as a unit, and here, of course, in the real case, it's not the case, right? So any subsequence here, even though from the second experiment, you can get the desirable results. The key here is that after many runs, you might have overlapping sequences, okay? So the another reason this naive understanding is wrong is that it does not consider overlapping sequence as we introduced earlier, right? So this, if it's the first 3, that does not match HTH. However, you don't have to start from scratch, right? The fact that you have HT here allows you to have just another H in order to see the pattern, right? So that's really important to understand, why this misconception number 1 is incorrect. So the second misconception is that since the coin is fair, so each time it has equal opportunity H and T. So for a lot of things, it is exchangeable, right? So that's why people say, all right, so if I solve for one pattern with 3 length, right? So for example, if the average to run to see the first HTH is X, I expect that the average run to see HHH, because the length of the pattern is also 3, So I would get the same answer, right? So the fact is the answers are different. So why are they different? Are they supposed to be the same because the coin is fair and we can, a lot of times we can use exchange argument? The exchange argument can be true if you make a statement that HHH and TTT, the answer to the question, what is average runs to see the first appearance of HHH versus TTT, you can say they're the same because H and T can be swapped, right? If you imagine you conduct the same experiment, but always flip the results, right? So you can use that exchange argument. But if the pattern are different, right, the answer would be different. So it's come down to the fact that they would differ with different failures. Like for example, in the case we're looking for HHH versus HTH, right? And when you have, earlier as we said, alright, so if initially you have a pattern like T and H and T, okay, so this is considered failure for both patterns. However, for the second one, you have a better chance of getting that. For the first one, you have to restart, right? Because the fact that you have a T ruins the case, right? So you have to look for the first appearance of H. So that's kind of, you have a different reaction if you fail to see the patterns. The other thing is that the overlapping possibilities are different for different patterns. Like for example, if you have here, for any arbitrary patterns, yeah, okay, so if you have this, okay, for the second one, oh, it's really bad, you don't have anything, right? But for the first one, of course you have a pattern here, right? Now imagine if you do not have that, if you have here, then you can still find another pattern here, right? Matches, but for the first one, pretty much no sub pattern would matter. So the way they overlapped, the structure wise, they're different. Okay, so you're gonna expect different results. And the recovery from the bad start would be different, right? So for example, as I said, if you have a TH T, that's bad for both cases, but for the second case, you still have a better chance of getting another H, and then you satisfy the theme, right? But for the first one, for this pattern, you have to restart. Okay, so these are the intuition behind, the fact that they could have different results depending on different patterns. Okay, so the exchangeable argument can only be used if you flip the pattern. Like for example, the answer for HTH versus THT can be the same, okay, using the exchange argument or symmetric argument. In earlier video, we know that the answer to get HHH on the average is going to be 14 runs. Okay, so today we argue that HTH, the answer is indeed different. The answer is actually 10. Okay, so as a review, let's try to use two different methods as in the previous video. Okay, so I strongly encourage that you go back and check out the original video on what is the average runs to get the appearance of HHH in a row. Okay, the first appearance of that. Do check out the video, make sure you understand different methods, and here come back and let's work out the answer for different pattern here. Okay, HTH. Now in the first approach, we're going to use recurrence. On what? On the unknown value. All right. So So the value x is the expected answer here, right? Expected runs to first see HTH. Okay? So the way to derive the recurrence is to figure out different possibilities by drawing out a tree. We try to list out all the possibilities in a tree structure and then derive a recurrence relation on X. All right? So initially, you may start with you have half chance to get H, which is desirable, and half you get a T. Right? Once you get H, you get half a chance to get a T here, right? And then you get a half chance at each time you get an H, right? You get an H. And here you could get a T here. You always have equal opportunity to get H and T, right? And here, once you get a T, you have to restart because we're looking for HTH, right? For the second H, right? If you get an H, you may get another H, which is bad because it's only useful for this H, right? The first H cannot be a subsequence. And if you get a T here, you might have a better chance because you already have 2 of the 3 sequence. So if you get an H, you're happy. So this is a happy state. Right, and notice that at each step is 1/2, 1/2. This is 1/2, right? So let's consider the leaf states, right? What are the possibilities? So here, this is p equal 1/2. This because we have 2 steps. This is 1/4. These 3 steps, p equal 1/8. That's p equal 1/8, right? So let's try to get a recurrence on the x. From here, you have half chance to get here, but then on the average, it takes another x times to get the happy state. For the recurrence, we can say x would equal half the chance that you get a t here, and then you wasted 1 step, you still need x to get there. Alright, that's good. And let's look at this one. This is happy, right? You have 1/8 chance to get here, and then the steps you have taken is 3. Okay, and for this one, right? So you have to restart. However, you wasted 3 times already, right? So what you do is 1/8 and then x plus 3. All right. Now this is a tricky part, which is different from the first video. If you have another h for the second h, so for easier argument, we're going to introduce another variable called y. So y is the average runs in order to get the final state if we have the first h. The average runs to get desirable pattern after the first h. Okay, so here what we can do is the fact that here it takes y steps to get happy state, right? So this probability is 1/4. So plus 1/4, and then you already taken 2 steps, and you still need y steps, right? Because the reason you have taken 2 steps is because you have initial h and another h. So you wasted 2 steps, and on this state, on the average, takes y steps. Okay. But we have 2 unknowns. We only have 1 equation. That's not enough, right? So another equation is regarding the initial analysis, right? So the initial analysis is that you could have h, you could have a t, right? With half chance, right? So it's going to be 1 plus x, similar argument, because you get a t here, right? But if you get an h, you can argue that from this state, on the average, it takes y steps to get to the happy state. And so here the recurrence is that it takes you have half opportunity, and then you wasted one step, but then you need y additional steps to get happy state. Okay, now we have two equations, right? Two unknowns. We can solve the equation. So let's do that. So let's call this equation 1, this equation 2. So for the equation 1, you multiply 8 on both sides, right? So let's do that. So equation 1, so 8x equal, that will be 4 plus 4x, 4 plus 4x, and then this would be 3, that will be 3, this would be x plus 3, okay? So it can be x plus 6, right? And this would be times 8 would be 4 plus 2y. Further simplification, here you have x, you have 4x, and this is going to be 5x, and then you have 3x, right? So 3x on the left hand side, and for the constant you have 4, and you have 14, yeah, and you have 2y. Alright, that's good. Now for equation 2, what you have here is you multiply 2 on both sides, so this is going to be 2x, and here you have 1 plus x and 1 plus y, so 2 plus x plus y, so which means you can cancel x, and you multiply this by 2, you have 2x equal 2y plus 4. And then for these two equations, you do the subtractions, right? The left hand side would be x, one side 2y would cancel, 14 minus 4, that would be 10. So x equal 10. So that's the answer. And we use recurrence by analyzing different transition probabilities, right? So this is a recurrence on the unknown value we try to solve. Now the trick here is that to introduce another unknown, which is what is number of runs in order to get the happy state if we first have an edge. Another way is use Markov chain. We can model the problem with different state, and we have transition probability, jump from one state to the other. Okay, so of course, so initially is empty state, epsilon here, right? So you get initial edge, you have a state where you see the initial edge, which is good, or you have t here, you see the t, each with probability 1/2, right? Once you get an edge, if you get another edge, you're going to stay in the same state because HH doesn't help. We're looking for HT, right? So here what you do is you have transition to yourself. If you get a t, however, you want to define a new state, right? So if you get a t here, you want to get a state which is HT. And then of course, if you get an edge, you're lucky. You get an HTH, that's accept state. Okay. And of course, for the other case, let's say on this HT, if you get a T, right, then you run the sequence, it's as if you get initial T. So you jump to this state here. On this state, if you get a T, you go back to yourself, right? So you go back to yourself. If you get a T, and if you get an H, you can jump to this state here, where you get an H. Okay. So on this state, if you get an H, you go back. If you get a T, so here you got an H, got a T. Here's the accept state. That would complete the diagram here. Let's mark out. So this is where you get another H. The different probabilities. Every probability, of course, is 1/2, right? This is 1/2, and this is 1/2 also, right? So for the Markov chain, we're gonna need linear equations, but we're gonna have multiple variables. We're gonna have variable x0, meaning from this state on the average, how many times to reach the happy state, right? And for this one, let's mark it, x1, from each state, what's the distance to the other one? Now, this would be, let's say, h2, and this would be h3. Okay. What is x0, right? We know that from x0, you have half and half transition, right? So you go to h where it takes x2 steps to reach to the happy state, right? So it's 1/2 1 plus x2, and then similarly, if you get a t here, is 1/2 x1. This is x1, right? So you write this recurrence for each state, right? So this from the x0, you're going to write x1 because for the x1, you go back to yourself or you go back to x2, right? So what happens is you can say x1 should equal to 1/2. You go back to yourself, you take another x1, or you go to x2, yeah? Now for x2, look at the transition, you go back to yourself and go back to this next one. And so in that case, x2 here, right, is 1/2. You go back to yourself, or you go back to the, maybe a little better state, ht, right? So you take x3 to get there, right? x3. If you are at x3, right, you got a half chance to go to the happy state, and if you got t, you take x1. So you have another, let's write it here. So x3, you have half of chance where you only take 1 step to go to the happy state, or half of chance and you go to t where you would take x1 steps to get to the happy state. Okay, so we have 4 equations, 4 unknowns. Of course, you can solve for x0 or skip the steps, and then that should give the answer x0 equal to 10. All right, so this is just a recap of what we did in the previous video. So think about the steps and think about why the misconceptions here are indeed incorrect. All right, so that may help you if the interviewer would ask you, conceptually, how to explain the fact that we get different answer if we try to find the first appearance of HHH versus HTH, right? The answers are 14 versus 10, right? And why it takes longer to get HHH, right? You can think about that. So for the consecutive sequences, mixed one is always easier to get than the pure, like for example, all straight edge, right? So you can expand this problem to 4 subsequences, but the math may be more tedious. To work out the length 3 pattern is probably a better option. So I hope you enjoyed the video. Please like, share, and subscribe to the channel.